Hello and welcome to the second in our series of videos looking at IPv4 subnetting. My name's Kevin Large and I'll be your instructor for this session. In this video we're going to be looking at the IP address classes and also the default subnet masks. In order to do this, we'll start off with the format of an IPv4 address. That's both the way the computer sees it in binary and also the way that humans represent it in so-called dotted decimal. We'll move on to look at the 5 IPv4 address classes. These are the Class A, the Class B, the Class C addresses. The first 3 classes are used for what's known as unicast transmission. This is a single host to a single host on a network. The Class D address, which is used for multicast transmissions, which is a single host to a group of hosts on a network. And if you enable multicast routing, it can go well beyond that network. And also the Class E address, which was originally reserved for experimental purposes. We'll also look at the default subnet masks that are associated with the Class A, B and C addresses. Okay, so what does an IP address look like? Well, to a computer, an IP address is simply a string of 32 binary digits, or 32 bits. This is perfectly good for a computer to work with, because they're built using millions and millions of transistors, so they're used to dealing with binary, but it's very difficult for a human to remember 32 bits in a row like that. You imagine trying to remember half a dozen IP addresses in that format. It would not be very easy to do. So what we need to do is we need to think of a way of representing those IP addresses. But before we move on to that, how many possible IP addresses can you have with 32 binary digits? Well, that's actually a very easy piece of maths. They're 32 binary digits, so the base is 2. There are 32 of the digits, so it's raised to the power of 32. So simply 2 raised to the power of 32 will give you 4,294,967,296 possible combinations of ones and zeros with 32 bits. That's how many IPv4 addresses exist. Now, to be fair, not every single one of those can be used as an address. But when you think about it, that's just a little over 4 billion addresses, and there are over 7 billion people on the planet. So, Houston, we have a problem. And this is one of the reasons why IPv6 was developed. Okay, moving on. How do we represent an IPv4 address in a format that's a little bit more human-friendly? Okay, the first thing we need to do is break down the 32 bits into 4 8-bit octets. Now, in programming or computer science, you probably call 8 bits a byte, but in networking it's generally referred to as an octet. So all we've done is we've simply broken the 32-bit string into 4 8-bit octets, and then we convert those octets into the decimal equivalents. So the first octet converts to 192, the second one converts to 168. The third octet there, that only has the 8-bit and the 2-bit set to 1, so that becomes 10. And the final octet only has the 1-bit set to 1, so that becomes 1. So we're actually looking at exactly the same IP address in its binary format and also in what's known as dotted decimal. Okay. Classful networks. So what exactly is a classful network? Well, there are 5 IP address classes, and these were used really from September 1981 when the Internet Engineering Task Force released its Request for Comment, or RFC 791. This defined the first 3 address classes, the Class A, the Class B and the Class C, and a little bit later on the Class D multicast address and the Class E experimental addresses were added, and they were in use up until approximately 1993 when something known as classless interdomain routing, or CIDR, was developed, which allowed us to use subnet masks of pretty much any size we liked, as long as they were contiguous ones in the subnet mask. Okay, so classes A, B and C, the original classes developed on RFC 791. These were widely used for unicast transmissions. Again, that is a single sender to a single receiver, or a one-to-one transmission. The Class D address range was used for multicast transmissions. This is a single sender to a group of receivers, one-to-many. This was widely used for streaming audio and streaming video. So you could put a multicast or Class D IP address on a device and it would join a multicast group. and you could simply stream audio or video to that entire group of machines instead of having to do it in a one-to-one basis. And then we have the Class E addresses, which were originally reserved for future use or experimental use. Okay, so that's the address ranges, but what does that actually mean? Well, the Class A addresses, there are only 128 of those, and each one could theoretically, and I do say theoretically, hold 16,777,216 addresses per network. You would never, in your wildest dream, try to put that many computers on a single network. In fact, you wouldn't even approach the tiniest fraction of that many computers on a single network. But theoretically, each one of those 128 networks could hold over 16 million addresses. We have the Class B range. There's a lot more of those. There's 16,384 of those networks, and each one could theoretically hold 65,536 addresses. Then we have the more familiar Class C address range. There are over 2 million of those networks, and each one could theoretically hold 256 addresses. Now I say theoretically because on each one of those address ranges you do actually have to remove two. You have to remove what's known as the network address and the broadcast address, but we'll get onto that in a little while. Okay, so if we look at the Class A range, the Class A range ranges from 0.0.0.0 to 127.255.255.255. It does depend slightly on the textbooks you look at. Some textbooks will say it starts at 1.0.0.0 and ends at 126.255.255.255, but most textbooks would regard it as being the way it's shown in this slide. And mathematically, in binary, you'll see why. If we convert those dotted decimal numbers into binary, you'll notice something about those numbers, something that stands out, partly because I've coloured it in red and underlined it, but both of those addresses, the lowest Class A address and the highest Class A address, they both start with a 0. And that's what defines a Class A address. If the most significant bit in the first octet, the left-hand most bit, is a 0, you're looking at a Class A address. And that's why we have those somewhat unusual numbers, ranging from 0.0.0.0 all the way up to 127.255.255.255. Okay. What does that mean then, if we're using a Class A address? Well, all it means is that the first octet defines the network, and the remaining 3 octets define the hosts. Okay. And of course, an IP address on its own is not really a great deal of use. We need to have a subnet mask that goes with it. So what's the default subnet mask for a Class A IP address range? Well, if we're dealing with a Class A IP address, all we need to realise is 1. The first bit in binary is going to be a 0. 2. The first octet is network, the remaining 3 octets are host. And to generate the default subnet mask, we simply set all the bits to 1 in the first octet, because 1s represent networks, and all the bits to 0 in the remaining 3 octets, because the 0s represent the host octets. So you have 1 network octet, 3 host octets. The network octet, all bits set to 1, which generates us 255, and the remaining 3 host octets, all bits set to 0, which gives us 0.0.0. So there is the default subnet mask for a Class A IP address. If we take a representative Class A IP address, we'll just say 10.1.1.4. That's a perfectly valid Class A IP address. And we apply the subnet mask, the default subnet mask for that address, 255.0.0.0. What does that actually mean? Well, for one thing, writing down 8 1s followed by 24 zeros is a little bit long-winded. So we don't really want to write the subnet mask down in binary format. We could use dotted decimal format, 255.0.0.0. That's a little bit better, but we can do better than that. We can actually use what's known as CIDR notation, which is where we basically count the number of 1s in the subnet mask. And if you look at that subnet mask, you'll notice there are only 8 1s in that subnet mask. So this is also known as a /8 subnet mask. It's just a very neat way of writing 255.0.0.0 as /8. Okay, now going a little bit deeper into the binary, If you remember, we said there were only 128 possible Class A IP addresses. Why is that? Well, I hope from this slide you can see exactly why that is. The most significant bit, the first bit in the first octet, represents what class of address it is. It's a 0, therefore it's a Class A. This leaves 7 bits remaining in that first network octet. I've coloured them in green on this slide. Those 7 bits define the networks. Now if you have 7 bits in binary, how many combinations do you have? You have 2 raised to the power of 7, or 128 combinations. This is precisely why there are 128 Class A networks. It's clever, isn't it? And we have the remaining 3 octets set as host octets. 3 octets, 24 bits in total. So 2 to the power of 24 gives us 16,777,216 total addresses. This is where you get your 128 Class A addresses, each with slightly over 16 million addresses per network. But that's not all of the story, because if you remember, I said there was 2 addresses that you cannot use on every network. And those 2 addresses are the network address, which is defined as all host bits set to 0, and the broadcast address, which is defined as all host bits set to 1. In fact, if you look at a dictionary of networking terminology, they will say a network address is convert to binary, set all host bits to 0. A broadcast address is convert to binary, set all host bits to 1. And we can visualize that. If we move a little bit further, we'll see on the very next slide, I'm going to set all the host bits to 0 to generate the network address, and all the host bits to 1 to generate the broadcast address. But just to give you some idea, the proper calculation would be 2 to the power of 24 minus 2, minus the network address and broadcast address, which gives us 16,777,214 hosts per network. There you go. There's your network address. 10.0.0.0. What's so special about that address? Well, all host bits set to 0. Therefore, this is a network address. It is not a valid host address. You could not put this address on the network interface card of a PC using that subnet mask, because it would realize that that is a network address and it's invalid to go on an interface of a computer, or a router for that matter. And what's the other address that we can't use? It's the network address and the broadcast address. They are the 2 addresses that we cannot use. So what does the broadcast address look like? Set all host bits to 1, which generates 10.255.255.255. And there is your broadcast address. Again, this is not a valid host address. So you cannot use that address on the interface of a computer, for instance. In fact, a broadcast address, if you ping a broadcast address, then theoretically every computer that's switched on would receive that address and have to reply back. Although modern operating systems and modern networks, they don't really allow you to ping broadcast addresses very easily, because it can be used as an attack vector and cause all kinds of trouble. Okay, we've gone a little bit deep on the Class A's, so we'll speed up a little bit on the B's and the C's and the D's and the E's. So moving on, the Class B address starts where the Class A finished, 128.0.0.0. Goes all the way up to 191.255.255.255. How do we generate those particular numbers? Well, if you look at the binary, it's quite straightforward to see how it works. With the Class A, the first bit was set to a 0. That says this is a Class A address. With the Class B, the first 2 bits are set to the pattern 10, and that generates Class B addresses. We can see the lowest possible Class B address, 10 followed by 30 zeros, and the highest possible Class B address, 10 followed by 30 ones, which generates the 2 addresses on the screen there. So what does a Class B address mean? Well, with a Class B address, the first 2 octets are now the network, therefore there are a lot more networks available, and the remaining 2 octets are for hosts, therefore there will be less hosts. You can't kind of get something for nothing. As you increase the number of networks, the number of hosts per network reduces. If we want to create the default subnet mask for the Class B addresses, it's very straightforward. The first 2 octets are network, therefore we set the first 2 octets in the subnet mask to 1, and the last two octets to zeros, which generates a subnet mask of 255.255.0.0. And that's all there is to it. If we pick a representative Class B address, 172.16.10.10, that's a perfectly valid host address. We could put that on the network card of a computer with the default Class B mask. It would be fine. And what does that really mean? Well, that default Class B mask is 255.255.0.0, or in binary 16 ones, so we can represent it as /16, which is an awful lot easier to write. Now if you have a little look at the first two octets, which are the network octets, the very first 2 bits in red, we can't use those because they define what class of address we're looking at. But if we look at the remaining 14 bits in green, you'll notice 2 to the power of 14 gives us 16,384. This is precisely why there are 16,384 possible Class B networks. And if we look in blue, in the blue host octets, you'll notice we've got 2 full octets for host. That's 16 bits in total. So 2 to the power of 16 gives us 65,536 total addresses. But we mustn't forget we can't use 2 of those, the network address and the broadcast address. So in reality we have slightly less, 65,534 usable or valid host addresses on the networks, on the Class B networks. Okay, so let's have a little look. What would a network address look like for a Class B? Very easy to do. With a Class B default subnet mask, all we need to realise is the last 2 octets are the host portion, so we set the last 2 octets to zeros and it generates 172.16.0.0. This is a network address and you cannot use it on a valid host. So you couldn't configure this on the IP, on the interface of a computer, for instance. It wouldn't accept it. In fact, if you go into a router and you type 172.16.0.0 space 255.255.0.0, in other words a combination of the IP address and the subnet mask, and hit enter, the router will actually say bad mask, which in Cisco language basically says you've put either a network address or a broadcast address on the interface. Okay, moving on, we have the broadcast address. How do we generate the broadcast address? Very simple, set all host bits to 1, because that's the definition of a broadcast address. This gives us 172.16.255.255. Again, this is not a valid host address, so we cannot apply it to the interface of a PC, server, laptop, tablet, router. Okay, good. Class Cs. 192.0.0.0 up to 223.255.255.255. I think you see the pattern developing here. First 3 bits in the first octet, 110. That defines the Class C address. You probably see the pattern developing here as well. Network, 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 host. Okay, so the first 3 octets are now set for networks, which is why there are so many Class C networks. And the last octet, the remaining 8 bits, is the host octet, which is why each Class C network can only hold a small number of hosts. Excellent. So the default subnet mask, the first 3 octets are network, we set them to 1s. The last octet is host, we set that to 0, and it generates the default subnet mask of 255.255.255.0. Brilliant. Let's look at a representative Class C IP address, 192.168.12.10. That's good. That's a perfectly valid Class C IP address. That IP address, together with the 255.255.255.0 subnet mask, you could put that on a computer, no trouble at all. How can we represent that subnet mask in a slightly more compact and easy to write format? Well, there are 24 bits in that subnet mask set to 1, so that would be a /24 subnet mask. Fantastic. How many possible Class C networks do we have? Well, the first 3 bits in the first octet are reserved to specify what class of network we're looking at, which means we have 21 bits available for the network. So 2 to the power of 21, 2,097,152 networks. That's a lot of Class C networks. But each Class C network is actually relatively small. we only have 8 bits available for hosts, which means we have 2 to the power of 8, or 256 total addresses per Class C network. Again, we can't use 2 of those, which is all host bits set to 0, the network address, and all host bits set to 1, the broadcast address. So we have to remember to remove 2 from the total number of addresses to give us the total number of valid usable host addresses per network, which is 254. Okay, so if we set all the host bits to 0, we generate a network address of 192.168.12.0. If we set all the host bits to 1, we generate a broadcast address of 192.168.12.255. Excellent. Then we move on to the Class D address. This is slightly strange in comparison to the first 3 classes of addresses, because the first 3 classes are used for unicast, one-to-one transmissions. The Class D is used for multicast, one to a group of machines. You'll notice in binary, the first 4 bits are set to 1110, and this generates the numbers ranging from 224000, the lowest Class B IP address, to 239.255.255.255, the highest possible Class D IP address. Fantastic. Okay, notice there is no network portion. It's all hosts, because this IP address would go on your computer network card in addition to your normal IP address, and it would signify that you were now a member of a specific Class D or multicast group. And you could have audio or video streamed to that group Class D address, and if you're a member of that Class D address, then you will receive the audio or video. It's as simple as that. Okay, so Class Ds are reserved for multicast, and they're in that particular range. Final class of addresses, the Class E. It's basically everything that's left now. The Class E has a binary representation with the first 4 bits in the first octet set to 1s, which gives us a range of 240.0.0.0 up to 255.255.255.255. Host, reserved for experimental purposes. And they are the famous classes, the A, B, C, D and E, of classful IP addressing. Now, classful IP addressing is not very efficient, and it was superseded by classless interdomain routing, and you can see why. And this is the reason why. We have default subnet masks for each class of address. The Class A has 255.0.0.0 or /8. The Class B has 255.255.0.0 or /16. And the Class C has 255.255.255.0 or /24. When you're actually doing computer networking, you sometimes wish that you had a 255 button on your keyboard, because you type that number so often with subnet masks. So these are the default subnet masks for the different classes of address, and this is what they mean. The Class A's, they have over 16 million host addresses per network, which is a ridiculous number. The Class B's have 65,534 usable addresses per network, and even the Class C's have 254 addresses per network. Now this is a problem, because if you think about it, let's say you want 100 usable addresses on your network. Well, the most efficient way of doing it would be therefore to use a Class C. But a Class C with its default subnet mask of /24 allows you to have 254 addresses per network. If you only need 100, you're actually wasting 154 addresses. It's even worse. You imagine if you needed 500 addresses per network. Well, it's too big for a Class C, and you can't use 2 Class Cs because it's got to be in one network, so you'd actually have to go up to a Class B address range. If you only need 500 usable addresses and you need to use a Class B to get there, you're actually wasting 65,034 addresses. You can't do that sort of thing. So you can see why classless interdomain routing is such a superior way of going about things. That's something that we'll be looking at in the next video, classless interdomain routing. At the moment, that is the end of the classful addressing and default subnet mask video. Please tune in next time to have a little look at the next video, which will cover classless interdomain routing and what's known as variable length subnet masking, which is where we're able to use subnet masks other than the default /8, /16 and /24. Thanks very much for looking. I hope you found this video informative.